also going to share some content here. Okay, so I think that works. You can also switch to the camera, I think, if that works as well. So, okay, so just a heads up, I'm trying out a different tech setup today. I've been dealing with some overheating issues on the device I had used before, so I decided what I'm going to do is I purchased this Wacom tablet, and so it's sort of like a smart pen, but I'm using my office machine. So I'm hoping that reduces some of the issues that at least I've been having on my end, where halfway through the stream it's sort of like the camera kind of freezes, and so I'm hoping that sorts itself out. But if anybody has any technical glitches and whatnot as the class progresses, let me know. Okay, all right. So I have here a slight correction I need to make on my announcements. It says here that this has been graded and that the solution's been posted. That'll be a little bit later today. But I'm going to post the solution to Blackboard as soon as we get off of the line here. But that'll be up here in a bit. One thing I did want to mention is this right here. So the DOH program, or the co-op application program, that's due on Friday. So if anybody's interested in co-op, let me know. I think I think with the current application structure, used to be, I think, that you sent it into the department and then it got sent in. But if you have any questions, let me know. I can walk you through that. The application process is still the same, and it's pretty simple. Well, yeah. One of the other thing I did want to mention is we are getting to the point where we are having a celebration, and so Friday, February 19th is our first exam. And so one of the, if you remember last semester, I said, or we had, for those of you that had me for structural analysis, we had the break that was instituted. Then it was in late November timeframe, and it sort of came at the last minute. Assuming everything goes well and we stay on schedule, I'm going to have a break instituted after that exam. So assuming everything goes well, we won't meet the following Monday, and we'll just come back that Wednesday and hit the ground running with bolts. But I just wanted to throw that out there, and we'll discuss some scheduling and whatnot moving forward. Okay, let's actually start talking about some steel design, and let's get into design. This is design day. We're actually going to begin our first design, which is design of tension members. I want to make sure that we recap a couple of things, that everybody's good with LRFD limit states, the idea that we deal in factored loads and factored resistances, because that's kind of important for laying the groundwork for what we're going to talk about today, and that everybody's good with tension member limit states, okay? And what I really want to focus on today, or at least what's going to monopolize a good bit of our discussion, is this expression right here. Because remember, what we're doing here is we're saying that the effective net area is just the net area times our shear lag factor, U. And the issue here is that in design, we don't know these. We have no idea what's going on because we don't have a shape, right? So in analysis land, or rating land, whatever you want to call it, we have a tension member. We know the connection. We know the size. We know the steel grade. We know all of that. And then all we're trying to do is assess its capacity. In design land, all we know is what are the constraints we need to meet. We have an element that needs to be able to resist X amount of load and tension. Now select an element to resist that load. We're going to have to come up with some way of handling this, because we don't know what the member looks like. And so that's going to mean we're going to need to make some assumptions, and we're going to have to go back and verify those assumptions. And so that's something I want to make sure that you've got in the back of your head. So let's get right into it. Let's talk about design. And so we're going to develop some expressions for design, and then we're going to talk about our design assumptions and then how we check those assumptions throughout the process. So let me begin by some ground rules. So first off, we've covered tension member analysis. Given the details about a member, we can take that member and assess its performance under gross section yielding, net section fracture, slenderness limits, etc. We can handle that. Now we're going to discuss design, and to be clear, that means we want to select a member to safely resist those loads. So now we're in the business of picking members. Okay. Now before we begin, let me establish some ground rules, and this is going to be the case throughout this semester. Okay. Number one. We will always strive to select the lightest member possible, okay? And so what I mean by that is if I have a W18 by 35 versus a W10 by 49 versus a W8 by 24, which one am I going to pick? The first one, the second one, or the third one? If these were my options, what am I going to pick? Let's just make sure everybody's awake and paying attention here. Boom. Exactly right. So what I mean by that, by light, we're talking about that second member. And why are we going with the lightest element? Well, the lightest element means, when we say it weighs the least, what we mean is if I had to buy those and I was paying for steel on a per pound basis, element 3 is the cheapest. And so there's a direct correlation if I'm purchasing steel between what's the lightest and what's the cheapest. So that's why we go with this. Now, I want to be clear that while this is a primary motivating factor in design, it is not the only factor, okay? Let me give you an example. If I was designing this building has hundreds and hundreds of beams and columns and braces and what have you. And if every single element was designed with a unique cross-section and a unique shape, the contractor is going to be spending their time putting together a jigsaw puzzle, okay? There is something to be said about using either a reduced family of shapes or a reduced suite of shapes, where you might have an element here or there in the building that might be a bit over designed, but in the end the entire construction process is a bit simpler. And so in that environment, yeah, you might have a couple elements that are a bit oversized, but in the end even that family is selected based off of lightest weight. Now, the other thing I want to point out is the second bullet, which says that the problems are always going to contain some constraints to ensure that we all arrive at the same answer. If I said, okay, here's a problem, I want you to design a tension member that can hold up 300 kips. There's 25 people in this class. If I get 25 different answers and they'd all be right, or they could all be right. That's a little bit of a headache for me to grade. So some of the problems will have some constraints to ensure that we all arrive at the same answer. But even then, some of that is built in reality. I'll give you an example on that. So when you're selecting columns in a building, so you've got these vertical elements that are supporting the vertical load on the structure. We tend to hide those columns behind walls, and the architect comes in and says, you only have 12 inches of space to put that column. And so as the structural engineer, I'm going to be selecting a W12. That's all the space I have, right? And so that design problem might be select the lightest W12 shape to safely resist those loads. And so some of these constraints are honestly for my benefit so that we all arrive at the same answer. But some of them are, in the real world, between supply limitations and architectural constraints on your project, you are going to have constraints beyond just the amount of load that it needs to carry. So that's something to keep in mind. Okay, now let's get into developing some expressions, because this is about as straightforward as it can get. So far we have 3 different limit states that we've been considering. Okay, we've got gross section yielding, we've got net section fracture, and we've got slenderness. Okay, and so for each one of those limit states, what I want to do is I want to see, okay, what is the required section property of the shape in order to meet those limit states. And here's what I mean by that. So let's take gross section yielding. Okay, so we know that phi PN has to be greater than or equal to PU, right? So the design resistance has to be greater than or equal to the factored loads. And if we're talking about gross section yielding, phi-PN is 0.9 FYAG, and that has to be greater than or equal to PU. Well, if I'm in design land, okay, and I know the load, right? I know that. I know 0.9. Now FY can tend to be a constraint based on the type of shape. So remember, we've said that, if you're purchasing a W shape, more often than not, it's going to be A992. If you're purchasing an angle, it's going to be A36. So more often than not, we know the FY at the beginning of the problem. What we don't know is the AG. We don't know the gross area. So we can solve for what is the required gross area in order to meet this limit state, and we just divide, and we get this right here. So we just get that the factored load divided by 0.9 times Fy will give us what I'm calling AG design 1. And you'll see why I'm calling it design 1, because there's going to be a design 2 here in a second. So this is, let me see. Well, I'm going to get to that, Mr. I'm going to get to that here in a second. But just remember, I'm taking each limit state one at a time. So, handling it one at a time. Right now, we're talking about gross section yielding. And gross section yielding doesn't have anything to do with net area or shear lag or anything like that. Net section fracture is when we deal with the net area and deal with the U. So will I handle the bolt holes and stuff? I will here in a second. And that's actually kind of the big problem that we're going to have to deal with here in a second. But I will get to that. All right. Now, what about slenderness? Okay, slenderness says that L over R has to be less than or equal to 300, so I can solve for what is the required R in order to meet that constraint. So just as with slenderness, I can solve for a required R as well. So gross section yielding, I can just solve for a value. Slenderness, I can just solve for a value. Net section fracture, it becomes a bit trickier, okay? And Trevor's kind of getting onto that because because if we're talking about net section fracture, remember phi-PN is 0.75 FU AN times U. Now, FU, again, that's a material property. We can look that up. But what about net area and U? So net area is a function of the hole thickness, which we don't know because we haven't picked a member. So if we haven't picked a member, we can't figure that out, right? I mean, we can't solve for that, if that's what I'm saying. And especially, what if we have a staggered connection or anything like that? Like, that gets kind of tough, okay? The other thing we don't know is the shear lag factor, because the shear lag factor is a function of X bar. It's a function of the connection geometry in general, and we don't know that in the design phase because, again, we haven't picked a member. So in order to handle this, we're going to make a design assumption. And so what I'm going to say is this term, net area times U, which is the effective net area, I'm going to say that that's about 75% of the gross area, okay? That is a guess, okay? Instead of trying to handle the net area and the shear lag and try and come up with separate assumptions for each of those, I'm just going to say, you know what? Net area times U is 75% of the gross area. It's a guess, all right? It's not accurate. It's not exact, I should say. It's close enough for the design process, but it'll get us moving the ball forward, and you'll see how we're going to handle this design assumption here in a bit. So if we solve for the cross-sectional area, so now we've got phi-PN has to be greater than or equal to PU. So 0.75 FU, and then instead of net area times U, I'm going to say 0.75 times the gross area, that's got to be greater than PU. I'm just going to solve again for the gross area, and I'm going to get this. So now I've got an AG design 2, okay? And notice I've got the 0.75 squared because I've got two 0.75s. One comes from the phi, and one comes from this design assumption I've made. So I've got two different design assumptions, or two different gross area for designs. I've got the one that came from yielding, and then the one that came from fracture. And so what I'm going to do is take those and combine those into this. And so if I'm trying to come up with a value for design, I'm going to take the worst case scenario. And the worst case scenario is going to be just the biggest of those two fractions. And the biggest of those two fractions denominator since the numerator is the same. Hence why I've got the minimum there. Okay. So if I go through and define a step-by-step process, here's my step-by-step process for designing a tension member. So step one, I'm going to determine the factored load. Okay. The factored load, so that would be 1.2 dead plus 1.6 live, all of that, until I get a PU value. Okay, so that's going to be my step one. Step two is going to be to compute my two design parameters, my two design section properties. So that would be my radius of gyration, so just L over 300, and then AG. So AG would be PU divided by the minimum of what's going on here. Mr. Ball asks, will we always guess 0.75 AG? We will, and there's a reason why, and the reason why is, well, let me put it like this. It actually doesn't really matter what we guess because of step four. Step four is the most important step in this whole process, which is to analyze the shape, but just bear with me. So we're going to compute the AG and the R design, and I'll show you later why 0.75 is such a good value for an estimation. The manual even uses that in some places as an assumption. The manual even goes to 0.75 AG, and you'll see that later. Based on these two values and based on the problem constraints, select the lightest shape based on these two design values. So we'll go into the manual with this and find the lightest shape that we can that meets those requirements. And once we have a shape, we have to analyze that trial shape in order to verify its performance. Yes, yeah, and I'm going to get to that a little bit more here in a second. I'm going to refine what Mr. Blizzard's talking about here in a bit. Now, our final step, I think, is incredibly important. We need to summarize the results, and we need to compute the efficiency of the design. Okay, and efficiency is a little bit of a new term, so I'm going to kind of explain that a bit, but a little bit of clarification. So, step four is very critical in the design process because again, as Mr. Ball pointed out, we're guessing this net area and shear lag effect. We're just saying let's just go with 75% of the gross area. That's a guess, okay? So you definitely need to take that section that you obtain and recognize it's a trial shape. You need to analyze it to ensure it works. It might not. It very well might not. And when that shape doesn't work, and it's possible that it doesn't, go to the next heaviest shape and then analyze it again. And so we call that iteration. That's that iterative process of designs. And that can happen a lot in the design world in engineering, is that you make some assumptions, come to a trial solution, and then analyze that solution. If it doesn't work, you refine your design and then do it again. That's very common in the world of engineering. And so it's possible that doesn't work. Okay. Now, step five is, I mentioned something called efficiency, okay? Now, the formula for efficiency is really just taking the load and dividing it by the resistance. And I included an image of this. Does anybody in chat know what this is? I'm going to be upset if nobody knows what this is. Anybody get the reference? Wheel on Price is Right. And does anybody know how the wheel works? Does anybody remember this? No. Oh. Yeah. Yeah, so you spin the wheel, and the idea is that you collect it's like blackjack. There you go. It's like blackjack. So you collect your score, and the idea is to get as close to $1 or 100 without going over. So the idea is to get as close to 1 without going over. Efficiency is very much like the Price is Right. You want that number to be as close to 1 or 100% without going over. If it goes over 100%, then what that means is that the member fails, because if it's over 100, that means that the numerator is bigger than the denominator. And if this is bigger than that, that's no good, because that means that the section fails. Okay, so you never want the efficiency to be and you want it to be pretty close. A good rule of thumb is that if your efficiency is 90% or greater, then that member is probably the most economical selection. Now, as I said before, in step 4, you can analyze your trial shape and find that it doesn't work, and then you have to go to the next one. Well, in step 5, what if you get an efficiency of like 40%? Well, what that means is that your member is probably too good. It's probably like too heavy, and you should probably like back it down and check the next lightest shape. So if your efficiency is low, like pretty low, I'd evaluate the next lightest section. But I will never penalize anybody in this class if they calculate an efficiency and it's 92% and they say that's good, and I'm just going to go with that shape. So like spinning the wheel, we want that to be as close to 100% as possible, but without going over. All right, does that make sense? All right, okay, let's do some design. I want to select the most economical channel of A36 steel that to be used as a 21 foot long tension member. The channel will support service loads of 100 kips of dead loads, 120 kips of live loads, and the member is to be connected using 3/4 inch diameter bolts. Now, note the constraints in the problem. We're restricted to picking a C shape, okay? So we're not gonna go with any W shapes. We're only gonna select a channel, okay? Now, if you open up the manual, there aren't that many channels in the manual. And it's, in fact, if you go to the manual, there's only one page of them. And they kind of go, not, you know, all the way, but they kind of go increasing in terms of area. So it's pretty easy to hone in on the one that's the most economical. And so we're going to pick a trial shape, analyze it. And so a lot of the steps, particularly in step 4 and whatnot, are going to kind of go kind of fast because we've done a lot of this. And so let's design a tension member start to finish. Let's rock and roll here. All right, so give me one sec. All right. The technology is actually somewhat working well today. Is every, oh, hold on, I gotta share it over here. Sorry. Give me one second. Oh, stop that. Oh, goodness. That's not good. Give me one sec. That's a little better. Okay. As soon as I said that the technology was cooperating today, it stopped cooperating. Is everybody able to see the screen pretty clearly? Good deal. All right, that's what I like to hear. Okay, so what we're going to do is we're going to go through this process step by step, and I think you're, I think we're going to find this is pretty straightforward. Okay, so step 1, I'm going to walk you through it, but I'll need your help on some of the calcs. So first thing I'm going to handle this load a little bit. So step, so I'm going to do that first. Actually, you know what? Let's look at some, I don't want to use the term system parameters, but let's look at some, you know, material and connection details. Okay, so let's see here. We know that we're dealing with A36 steel. So if we're dealing with A36 steel, can somebody tell me what is going on with FY and FU? And FY is 36, FU is 58, and that is from table 2-4. So this is 36 KSI, and this is 58 KSI. Also, we know that we are dealing with, okay, so one of the things I kind of like to do is I kind of like to highlight all of the information in the problem to make sure I've sort of used it all. What about this 21 foot long piece of data here? So we know that the member is 21 feet long. And what should we do to that? Just so we're sort of all on the same page here. There you go. And so 21 times 12 is what? Like I said, I'm going to need y'all's help. 252. So 252 inches. All right. And so that takes care of that. And then while we're at it, we know that our bolts are 3/4 inches in diameter, and so we know that our effective hole diameter is what? There we go, 7/8. All right. So I think we're ready to start rocking and rolling. Let's go ahead and do step one. Step one is to compute our factored load. And so we know that PU is 1.2 P dead plus 1.6 P live. I mean, you know, normally we should go through all of these load combinations, but we got 100 and 120. I think we can by observation know that this is the one that's going to govern. And so 1.2 dead plus 1.6 live is going to be 1.2 times 100 plus 1.6 times 120. And so what are we going to get? Anybody got an answer for me? $312. Okay. Okay, that's what I got here too. And just let me know if there's anything that I messed up or whatnot. Let me know. Okay. Step two is to compute our design parameters. Okay, so here's how I'm going to go about this. First off, here off to the side, let's do some math. So 0.9 Fy is 0.9 times 36, which is 32.4. And then remember, our formula states that we don't do 0.75 times Fy. We do 0.75 squared times Fy. So don't forget that. Okay, so 0.75 squared. Sorry, and that's not Fy. That's Fu. All right. All right, so I'm getting 32.625. Can somebody check me on that? Make sure I'm doing that right. Okay, so therefore, we know our AG design is the minimum of these. Whoop. Under PU, which is just going to be 32.4 under 312. Right? Because between these, I'm going to go with that one right there. All right, so 312 divided by that. I'm getting... Oh, what are y'all getting? Somebody help me out. I'm not going to do all this. Somebody going to help me out with this. What you got? $9.63. There we go. Boom. Okay. And then our design is L over 300. Now remember, we already converted the L to inches, and that was, what was that? I think it was, yeah, 252 inches. .84. Boom. So what we're going to do is select a trial shape. Now, what's the deal with this trial shape? What do we know about this trial shape? Well, number one, it's got to be a C shape. It's got to have a gross area of at least 9.63 and an R design of 0.84. Now, let's talk about the R design. For a C shape, just somebody open up the C shape tables, table 1-5, and what should we be looking at? Should we be looking at RX here, or should we be looking at RY? Which one's going to govern? The RY. The RYs for the channels are always smaller. So RY. So somebody help me out. All right. Let's go through the manual and let's try what? What shape are we going to try? What shape has a gross area of at least 9.63 square inches and a radius of gyration along about the y-axis of 0.84? And I got a C15 by 33.9. All right. That's something. Is anybody else getting that? That's about what I'm getting. There we go. So there's our trial shape. Okay, so C15. All right. So let's write down some parameters. Let me ask you a question. What do we need? Like, I mean, if we wanted to analyze this, I'll give you two. I know we need the gross area, which is 10. That I know we need. We also need RY. I mean, we got to at least, like, why did we pick this? So RY 0.901. What else do we need? We need TW. Remember, if I scroll up, this section, the bolts are through the web, right? So here's the section. And we got bolts through the web. So we need the TW. He's exactly right. And so what is TW? I'm getting 0.4. Oh. All right. What other value? There's one more value that we ought to look up to do our analysis. Well, you're kind of a little bit closer on the right path, Zach, is U. But in order to compute U, what do we need? Tell you what. There you go. Because here's our shape. We need to know the distance from the connected face to the centroid. So we need the X bar connection, which for this shape is X bar. Now, Mr. Bauer, what were you referring to? Is that... Now, this down here, this is, let me write this down. 788. Oh, yeah, that's given, yeah. Okay. So yeah, so these are the parameters that we're going to need. We're going to need the X bar, the web thickness, and then we're going to need RY, and then this. So with that, we're ready to go ahead and start analyzing this section to verify its capacity. Again, we got to check it to make sure it works. All right, so I'm going to cheat here a bit. Okay. Let me move this over here. So step 4. Analyze. So we know the gross area really from an analysis perspective, beyond just computing the limit states directly. We need the net area and we need the shear lag factor. So let's deal with the net area first. So the net area is going to be the gross area minus how many bolt holes? How many bolt holes are we going to need to subtract in order to compute the how many bolt holes we're going to need to subtract from the gross area to compute the net area? 2. See, at this point, this stuff's going pretty quickly, and that's kind of what I like. I know that you all are firing this stuff off, and I kind of like it. So DE times the thickness, which in this case is the web thickness because the bolts are going through the web. So this is, I'm going to cheat here a bit. What is that? It's 10. I drew too many there. Minus 2 times 7/8 times 0.4 and get 9.3. Do I have a second on that? There we go. All right. Now we need our shear lag factor. Which cases are going to apply? So we're going to go to table D3.1 on page 16.1-30. So all the way back here in this part of the manual, you know, in our shear lag table. And we're going to ask ourselves which cases govern. So is it, are we going to do case 1, case 4? Somebody tell me which cases we're going to use. Just case 2, that's exactly right. We don't have a W section. We don't have an angle. Not all of the cross-section components are connected. It's just case 2. That's the only one. And so for case 2, we need X bar connection, and we need the length of the connection. Now, X bar connection, again, because we have a channel connected with bolts through the web, that's just X bar, which we looked up a little bit ago. And that's 0.788 inches. Now, what about the length? What is the length of this connection? 7 inches. No, oh, okay, here we go. All right, Mr. Bauer, he put 252 inches. So in this instance, whenever we do U, the U, U2 is 1 minus X bar over L. We're not talking about the length of the entire member, but just the length of the connection and the length of the connection. So in this instance, we're talking about this dimension as LCON. And that's only going to be 7 inches here. So don't get that one confused with the length of the entire member. Okay, and this is 1 minus 0.788 inches over 7 inches. Because again, when we're talking about shear lag, we're talking about the stress discontinuities over the connection region. So it would make sense that we're not using the length for the entire member, just the length where the bolts are. Okay, I think I saw in chat where somebody had an answer on that one. What we got? 0.887, and it's been seconded. Man, you all are rapid fire today. I like it. And there are no units here, so that's nice. So now we can go ahead and compute all of our limit states, or we can do them all right now. And again, it might seem like we don't need to do some of them. Like for instance, with gross section yielding, a common question I get is, do we really need to compute the gross section yielding if we didn't have to make any assumptions? Like we know the section meets gross section yielding. The answer is yes, because I want to compute the efficiency later. And for all I know, gross section yielding governs. It might not. And so the only way to really know is to just do them both. And also, I kind of like to just do the full-blown analysis, all the limit states. Just at the end, I can summarize and make sure it works, even the slenderness. So let's just do it all and do it right. So gross section yielding is 0.9 FYAG, and so that is 0.9 times 36 KSI times 10, and then net section fracture (0.75) FU net area times U, which is 0.75 times, what is that, 58 KSI, times the net area, which is 9.3, times U, which is 0.887. All right, and so let's see if we can list these. What are we getting for gross? I got 324. And what about net section fracture? So hold on, you might want to check your math on that. Hold on. Whoa. All right. There we go. Okay. So 358.8. So which one governs? Is it gross section yielding or is it net section fracture? It's gross section yielding. And so this is one of the reasons why you want to check gross section yielding. I know it might seem like you really don't need to, but without doing this, I don't think we really would have known whether or not it governed. And it's a quick calc. It's no real reason not to. While we're at it, let's do the slenderness check. So let's do L over R. So L over R is 252 inches over the RY, and the RY was, what was that? 0.901. And so what is that? 252 divided by 0.901, 279.7. And yes, you're right, it'll pass. We'll say 279.7. But again, I just think it's really good practice to just do them all. Okay? So let's make sure that we summarize everything and compute our efficiency. So step 5, summary. Oh. Hold on, I hear some beeps. Well, what we did is we computed the required. So what we did is we computed the required R value for design, and then we picked a member based on that R value. This is just me computing the L over R just to verify it's less than 300. Does that make sense? Yeah. So it's just me formally just taking the member and fully analyzing it just to make sure it works. And you'll see what I mean when I go through this summary here in a second. So let's look at our design summary. So we know that our factored load for this problem was, what was it? It was 312 kips. We know that phi PN was 324 kips. Okay, and that was based off of gross section yielding. We also know that our L over R is 279.7. So we know that that spec is met. And so usually what I'll like to do is I like to say, therefore, okay. In other words, we know that because that's less than 300, we know we meet that spec. Very last step is to compute the efficiency. All right, and I got a number there, so it's PU over phi PN, so 312 kips over 324 kips. And Trevor is telling me that I'm getting 96.3% or 0.963. Do I have a second on that? Okay, so is this a good design? I mean, I'm asking you, is this a good design? Yeah, that's pretty good. You know, that's pretty good. You know, it's over 90%. Also, because this number is less than 100%, like the Price is Right, got close as we can to 100 without going over, we know we meet strength limit states. We know we meet service limit states. So what's the answer to this problem? The answer is that. That's the answer. We started out this problem with a member. We didn't know what the member looked like, but we selected a member based on the problem constraints that could adequately sustain the load that was applied and could do so economically and competitively. We have a member that has efficiency well over 90%, but it hasn't failed. It meets slenderness limits. That's our answer. Whoa, what happened? My screen went blank. Hold on. There we go. I don't know what happened there. One step at a time. One step at a time. All right, any questions before we call it? All right, one thing I do want to mention before we do call it. So you have a homework assignment that's going to be very much like this. However, it's not a C shape. It's a W shape. Okay. So what that means is, and specifically, I think I limit it to a W8. I think it is. I think you're limited to selecting a W8. What is going to change? I mean, the whole process is going to be the same, but what is going to change is you're going to have a different U factor, because not only are you going to have case 2, but you're also going to have, I think, the case 7, because it's a W section connected via the flanges. So this part here, this part on the homework assignment is, there's going to be more to it. Okay. So it means you're also going to have to look up that equivalent WT and so on and so forth. So don't just, blanketly repeat everything that I'm, doing in this example. It's a different shape. So that part is going to be different. Other than that, it should be largely the same. Don't forget that the bolts are going through the flanges, not the webs. So the net area calc, make sure you're doing that appropriately. But if you understood this, then the homework assignment should be pretty good. And then on Wednesday, we're going to do another one. I've got another actually rolled shape example. We're going to go through that. I think Wednesday will go pretty quickly. And then on Friday, we're going to handle block shear. And then just so you're aware where this is going, once we do block shear, Monday we do threaded rods. And then Wednesday and Friday, it's celebration time. And so that's where we're at in the class, and that's where we're headed. Any quick questions before I call it for the day? All right. Well, I'm going to go ahead and... Next Friday. Like the night... Of course, that's exam 2. Exam 1's tomorrow. That's a joke. I'm just messing with you. It's okay. You're getting roasted in the chat a bit. All right. That's all I have, everybody. I'm going to stop the recording, and I will see you all on Wednesday.